Welcome back to the Deep Dive. Today, we're talking about the toolkit that's always there, under the hood. You know, if you spend your time writing classes, messing with data frames, building web stuff in Python.
You're leaning on these things constantly.
Right, constantly. And you might not even fully realize just how much power is packed into them.
We are talking about Python's built-in functions. They're like the core vocabulary of the language.
Always available, no imports needed.
Exactly, zero imports. And our goal today, well, we're diving into a list, a categorized list of over 50 of the most crucial ones.
50 plus.
Yeah, quite a few. Across about 7 main groups, things like type conversion, math, inspection, iteration, even execution.
Wow. Okay.
And the mission isn't just to list them. It's to give you, the learner, a shortcut, a way to really get how they work, and crucially, the little surprises, the nuances in the results, the gotchas. Precisely. Those tiny behaviors, you know, how a function handles a negative number or a decimal point, that stuff can make or break your code. It's the difference between solid logic and subtle, really annoying bugs.
Okay, so the big idea is fluency. Getting comfortable with these core features.
That's it. Leverage the core language. Your code becomes clearer, more idiomatic, easier for others to read, and faster. Way faster, often, because these built-ins are optimized down at the C level.
Right. So where do we start unwrapping this toolkit?
Let's start at the absolute base. Moving data around, changing its shape, type conversion.
Makes sense. Data rarely stays in one form for long, does it? Comes in as a string, needs to be a number, maybe gets chopped into a list.
Exactly. It's restless, which is why these type conversion constructors, they're usually the first things any Python dev really gets comfortable with.
Not the core ones.
We've got int, float, and stri. They let you shift between those like atomic data types. Pretty straightforward mostly.
Okay.
Well, here's our first nuance. Using int to convert a string number, like int123, that works just fine.
But what if the input is a float? Like say I have 456.78. If I call int on that, does it round? Like in math class, in 456.78 becomes 457.
Nope. And that's a really common assumption. Python doesn't round here. It strictly truncates.
Truncates, so it just cuts it off.
Exactly. Throws away everything after the decimal point. Doesn't matter if it's 0.1 or 0.9. So in 456.78 just gives you 456.
Okay, that's a big difference. Not rounding, just chopping.
Huge difference, especially compared to the actual round function, which we'll get to. If you're doing financial stuff or stats, not knowing this could subtly mess things up.
Good to know. So after the basic types, we get into collections, list, tuple, dict, set.
Right. And the cool thing here is they work on pretty much any iterable object. They can break things down.
How so?
Well, when you convert something, you're usually iterating over its pieces. So if you give list the string hello, you don't get a list with just hello.
You get the individual characters.
Exactly. You get Same idea applies to tuple. Takes an iterable, makes an immutable sequence out of its parts.
But dict is a bit pickier, isn't it?
It has to be, right? A dictionary needs structure. It needs keys and values. You can't just throw a list of numbers at it.
So what does it need?
It needs an iterable where each item itself contains 2 items, like an iterable of pairs, usually tuples or lists. The classic example is a list of 2-item tuples, A1, B2.
Okay, that list of tuples.
It gets correctly turned into the dictionary, A1, B2. Understanding that key value pair requirement saves a ton of headaches when you're parsing data.
Definitely. And then there's set, which is kind of the champion of data cleaning.
Oh, absolutely. It's a workhorse for deduplication.
Yeah.
Its whole reason for being is unique items. You feed it something with duplicates, like 1, 2, 2, 3.
It just gives you 1, 2, 3, kills the extra 2.
Instantly. Super efficient way to find all the unique things in any collection. One line.
Okay, let's dig a bit deeper conceptually. Talk about bool and this idea of truthiness.
Ugh, truthiness. Yeah, this is super fundamental to writing, Pythonic code. We all know bool 1 is true and bool 0 is false.
Right.
But the concept of falsy values goes way beyond just 0. Any empty container, falsy.
Okay.
Empty string bool is false.
Empty list bool.
False. Empty tuple, empty dictionary, none. All false.
Why is that so critical for a developer to grasp?
Because it makes conditional logic so much cleaner. Instead of writing, say, if lend-me list is 0 to check if a list has items.
You just write if my list.
Exactly. Python handles the truthiness check implicitly. Any non-empty collection, any non-zero number, any non-empty string, they all evaluate a true. It's a huge part of Python's readability and if statements.
That's really core stuff. But type conversion isn't always high level, right? Sometimes you need to get down to the byte level.
Absolutely. Networking, security, messing with binary files. You need bytes. and byte-array.
So how do those work?
Well, data moving in or out of your system is usually raw bytes. If you create bytes from a string, you must tell Python the encoding, like bytes. Hello, Adifate day.
And that gives you...
Hello, see that little B prefix? That tells you it's raw bytes, not a text string.
And byte-to-rec.
That's for when you need those bytes to be mutable, changeable. If you need to tweak individual bytes in memory, like modifying a file header or a network packet, bycorrect is what you use.
Got it. Okay, quick mentions for the specialty types. Complex.
Yeah, complex is for complex numbers, mostly science, engineering. You can make one with real and imaginary parts, like complex 1, 2 gives you 1 plus 2j, or parse it from a string-like complex, 3 plus 4j.
And frozen set. You mentioned that connects back to sets.
Right, it's like set. It removes duplicates. But the key difference is it's immutable. You can't change it once it's made.
And why does that matter? Why have an immutable set?
Because immutability means it's hashable.
Ah, hashable.
Meaning it can be used as a key in a dictionary or an element in a set. A regular set can change, so Python says, nope, can't use that as a dictionary key. But a phrase and set is stable, reliable, so it can be a key. Perfect if you need a unique collection itself to be the key for something else.
That's a neat connection. And a good transition, actually, from data structure integrity to,
well,
doing math with it.
Yeah.
#tag2. Mathematical operations and precision.
Okay, math functions, moving beyond just plus list.
The simplest one is probably abs,
Mm-hmm.
right? Just gives you the positive version of a number.
Yep, abs 5.5 is just 5.5. No surprises there.
But then things get more interesting. You mentioned efficiency functions, like divmod.
Ah, divmod. Yeah, I like this one. It's efficient because it does two things at once. Integer division and the modulus remainder. It returns both the quotient and the remainder together in a tuple.
So divmod 10, 3 would give.
3 as the quotient, 1 as the remainder. Straightforward for positive numbers.
But I remember hearing there's a twist with negative numbers. What happens with, say, divmod 10, never 3?
This is where it gets tricky. A common pitfall, actually. You might expect, what, never 3, 1?
Yeah, maybe. 10 divided by -3 is roughly -3, remainder 1.
But Python gives you never 4, never 2.
Whoa, okay. Quotient method 4, remainder for never 2. Why?
It comes down to the mathematical definition Python uses. The rule is 1 equals q times b plus ron. Divided equals quotient times divisor plus remainder. And crucially, Python guarantees the remainder r always has the same sign as the divisor b.
Ah, the divisor here is -3. Negative.
So the remainder must be negative, or 0. It can't be 1. To make the equation work with a negative remainder, the quotient has to adjust.
What do you think? -4 times -3 is +12.
Right, and 12 plus -2 equals 10. The math works out, but only if the remainder takes the sign of the divisor.
Okay, that's subtle but critical if you're doing anything with cycles or indexing where you rely on that remainder behaving consistently.
Absolutely vital. Now, another function with a dual personality, pow.
Power, like exponent.
Exactly. 2 arguments. Pow2, it's just 2 to the power of 3, gives you 8. Simple.
But the 3-argument version.
That's where the magic happens for certain applications. Pow base exponent modulus, it calculates base exponent percent modulus, so pow 2, 3, 5.
That's 23 per 7, so 8%, which is 3.
Correct. And this modular exponentiation is way more efficient than calculating the full power and then taking the modulus.
Why is that?
Because it keeps the intermediate numbers small. Imagine raising a huge number to a huge power. The result could be astronomically massive, taking tons of memory and time. The 3-argument pow does the modulus reduction at each step of the exponentiation calculation.
Keeping things manageable.
Exactly. Essential for things like cryptography or working with really large numbers where the full intermediate result would just be too big.
Okay. For collections, we have the basics. Min, max, sum.
Pretty straightforward. Min and max find the smallest or largest item. They can take an iterable, like a list, or just a bunch of arguments directly, like max, 10, 52, easy.
And sum. Any quirks there?
Just one useful feature. It takes an optional second argument, which is the starting value for the sum. Normally it starts at 0. But if you do sum 1, 2, 3, 4, 10.
It starts adding from 10. So 10 plus 1 plus 2 plus 3 plus 4 gives 20.
Right. Handy if you need to add to some existing baseline value.
Okay, now, the function that causes the most double takes. Round.
Right.
We know round 3.141592 gives 3.14, and that makes sense. But the tie-breaking rule in Python 3 It's weird, right?
It's not intuitive if you learn standard round half up. Python 3 uses round half to even, sometimes called banker's rounding.
Round half to even. So what happens with something exactly halfway, like 3.5?
It rounds to the nearest even integer. The nearest even integer to 3.5 is 4. So round 3.5 gives 4.
Okay, that one went up. But what about 2.5?
The nearest even integer to 2.5 is 2. So round 2.5 gives 2.
It goes down to 2. Wow.
Yeah. Counterintuitive at first glance. The idea is statistical. If you always round 0.5 up, you introduce a slight upward bias in large data sets. Rounding to the nearest even means sometimes you round up, sometimes down, balancing it out over time.
So it's for mathematical rigor, especially in finance or science, even if it trips up beginners.
Precisely. It prioritizes correctness over common convention. And it perfectly shows why knowing just the function name isn't enough. You need the details. Hashtag tag 3, input output, and fundamental object inspection.
Okay, shifting gears slightly. Let's talk about how programs, interact, input, output, and looking at what things are.
Right. Communication and basic inspection.
Communication starts with print, obviously. Everyone's first debugging tool.
Yeah.
To showing stuff on the screen.
Absolutely. Text, variables, whatever you need to see. And the flip side is input. Getting data from the user.
How does that work again?
Input basically pauses your program. It shows a prompt message you give it, like, please enter your name. Then it just waits for the user to type something and hit enter.
And whatever they type.
Gets captured and returned by the function as a string. Always a string. Even if they type 123, you get the string 123.
Ah, so you'd need to convert it with int or float if you wanted a number?
Exactly. The example showed capturing AI, G or RU, and then using it in a greeting. Standard stuff, but that always returns a string part is key.
Okay, so once we have data, we need to inspect it. Len seems like the main workhorse here.
Totally. Len just tells you the size, the number of items, works on strings, number of characters, lists, number of elements, dictionaries, number of key-value pairs, tuples, sets, pretty much any container.
Len low is 5, len 1, 2, 3 is 3. Simple.
Yep. And then there's type, which is essential for debugging.
Just tells you what kind of thing a variable is holding, like class int or class list.
Exactly. Helps you confirm your assumptions when things go wrong, which leads us to a slightly more abstract function.
Right. Not what it is, but where it is in memory.
Precisely. Len gives you a unique integer representing that object's specific location in your computer's memory at that moment. Understanding id is really key to understanding how Python manages memory, especially around mutable versus immutable objects.
Let's look at that contrast again. Small immutable numbers first.
Okay, if you do A1 and then B1 and check IA and IAB.
They're the same ID.
They are. Because Python does this optimization called interning for small integers and some strings, it sees they're identical and immutable, so why waste memory? Both A and B just point to the same single one object in memory.
Saves memory, makes comparisons faster.
Yep. But now consider mutable objects like lists. If you do C12 and D equals 1, 2, the contents look the same.
But IDC and ID will be different.
Guaranteed. Because lists are mutable, you might change C later, maybe append a 3. That change should only affect C, not D. So Python must give them separate identities, separate locations in memory right from the start.
That distinction is fundamental. Mutability directly impacts identity and memory.
It really demonstrates Python's underlying object model. Hashtag tag PS. Advanced object introspection and manipulation.
Okay, let's step up the complexity. Introspection where code can examine and even change other objects while it's running, starting with dir.
Right, dir. Think of it like an X-ray for your code's environment or objects.
How does it work?
If you call dir with no arguments, it lists all the names currently available in your main scope variables, functions you've defined, modules you've imported, everything visible right there.
And if you call it on an object, like dir my list,
then it gives you a list of all the attributes and methods that specific object has access to, all its capabilities. You'll see standard methods like append for a list, but also the dunder methods, the special ones like init or len. It's a complete inventory.
Very useful for exploring. Now, for actually changing things dynamically, there's that quartet. Getter, seditor, seditary delator.
Yeah, this is where things get really dynamic. The key here is that you're interacting with attributes using strings containing their names, not the usual dot notation like object.attribute.
Why would you do that?
Think metaprogramming, building flexible frameworks, maybe reading configuration where attribute names aren't known until runtime. You read a name from a file, then you use getter to get the value of the attribute with that name.
So using the myClass example from the source, if my object has an attribute called value.
Instead of myObject.value, you'd write header myObject value. Pass the object and the attribute name as a string.
And Citator lets you change it.
Yep. Citator, my object value 200, would change that attribute's value, again using the string name.
Hesseter is for checking first.
Exactly. Good defensive programming has a tar, object, some attribute name, returns true or false. Lets you check if an attribute exists before you try to get or set it, preventing errors.
And delatter removes it.
Right. Delatter, some object, attribute move, dynamically removes that attribute from that specific object instance. Poof, it's gone. This whole set gives you incredible runtime flexibility.
Okay, moving on to checking type relationships more formally. An is_subclass is generally the preferred way to check an object's type, especially with inheritance involved. It asks, is this object an instance of this specific class or any class that inherits from it?
So more flexible than just checking type is. Much more flexible, yeah. 1, 2 is an instance of list. Is_subclass is specifically for the inheritance hierarchy itself. Does child class inherit from parent class? Is_subclass, child class, parent class, tells you true or false.
And the source highlighted a key point about the ultimate base class.
Ah, yes. Everything in Python, ultimately, inherits from the base object class. No matter what class you create, is_subclass, your class object, will always be true. It's the root of the entire class tree.
Good to remember. Lastly, for this section, checking behavior.callable and hash.
Callable is simple. Can this thing be executed like a function? If it's a function, a method, or even a class, which you call to create instances, callable returns true. If it's just data like a number or a list, it's false. Useful for generic code that needs to handle both actions and data.
And hash, we touched on this, it's the gatekeeper for dictionary keys and set elements.
Exactly. To be efficiently stored and looked up in a dictionary or set, an object needs a consistent hash value. Immutable things, tuples, strings, numbers, frozen sets, have reliable hash values because they can't change.
So hash 12 works.
Yep. But try hash 12 on a list.
Type error, because lists are mutable.
Right. If a list could be a dictionary key, you could put it in, then change the list contents later. The original hash value would be wrong, and Python would never be able to find that key again. Chaos. So, hash enforces that only immutable, hashable things can play those roles. Hashtags tag V, iteration, and data pipelines.
Okay, let's talk about making programs do things repeatedly. Iteration. We all use for loops, but what's really going on underneath?
The magic behind the loop. It relies on two core built-ins .iter and next. This is the iteration protocol.
How does it work?
When you write for item in mylist, the first thing Python does internally is call iter mylist. This creates an iterator object. Think of it as a little machine that knows how to give you the items one by one and remembers where it is.
Okay, so iter creates the iterator.
And then inside the loop, Python repeatedly calls next on that iterator object. Next myIterator asks for the very next item.
So if our list is 10, 20, 30, the first next gives 10, the second 20, the third 30.
Precisely. The iterator keeps track.
What happens when you call next after the last item, when it's empty?
This is the crucial part. It raises a specific exception. Stop iteration.
An exception, like an error.
Well, yes, but it's an expected one. The for loop machinery is designed to catch this specific stop iteration signal. That's how it knows the sequence is finished and it's time to stop looping. It's not an error you usually handle yourself, it's the loop's termination signal.
Huh. So the loop relies on that exception being raised. Interesting.
Understanding iter and next lets you build your own custom objects that can be looped over.
Now, for more standard looping, especially when you need the index number, there's enumerate.
Oh yeah, enumerate is a lifesaver. So much cleaner than setting up a counter variable yourself.
How does it work?
It takes an iterable like apple, banana, cherry, and as you loop, it gives you back pairs, the index and the value. So you get 0, apple, then 1, banana, then 2, cherry, index and value bundled together automatically.
Much cleaner. Okay, let's get into the functional programming style tools. Map, filter, zip.
These are really powerful for creating data processing pipelines, and they often use lazy evaluation.
Lazy evaluation.
Yeah.
Meaning they don't do all the work up front.
Exactly. They usually return an iterator or generator. The calculations only happen when you actually ask for the next item, which can be way more memory efficient for large data sets.
Okay, so map, what's its job?
Transformation.map applies a given function to every single item in an iterable. The classic example is squaring numbers. You map a function like lambda x dot by 2 onto 1, 2, 3, 4, 5, and you get back an iterator that will yield 1, 4, 9, 16, 25.
Applying one operation to everything. And filter.
Selection.filter keeps only the items that satisfy a condition.
Oh.
You give it a function that returns true or false. Filter yields only the items where the function returned true.
So filtering a list of numbers for even ones, lambda x x% 2 equals 0.
Would give you back an iterator yielding just 2 and 4 from our example 1, 2, 3, 4, 5. It picks out the ones that match, often much clearer than a complex list comprehension.
And zip brings things together.
Yep, in parallel. It takes multiple iterables and pairs up their corresponding elements. If you zip 1, 2, 3, A, B, C, you get an iterator yielding tuples. 1A, then 2, then 3C.
What if the lists are different lengths?
Stops as soon as the shortest input iterable runs out. Really handy for processing related columns of data together.
Okay, last one for iteration. The common range function.
Mm-hmm.
We use it all the time, but maybe don't appreciate its flexibility.
Right. Most people just use range 5, which gives you 0, 1, 2, 3, 4. It defaults to starting at 0 and stepping by 1.
But you can give 2 arguments.
Yep. Range, start. So range 2, 8 gives you 2, 3, 4, 5, 6, 7. Note that it stops before the stop value.
And the 3-argument version adds a step.
Exactly. Range, start, stop, step. This is powerful.
Yeah.
Range 10, 2, -2 lets you count down by 2s. 10, 8, 6, 4. You can skip items, go backwards. Very flexible for controlling loops. #tag16. Execution, evaluation, and practical utilities.
All right, now we're getting into some seriously powerful territory. Functions that actually execute code dynamically.
Mm-hmm.
A big warning label on these, right? Evil and exec.
Oh, absolutely. Huge caution sign. They are incredibly powerful, but they open up massive security holes if you're not extremely careful, especially with any kind of external input.
So evil first, what does it do?
Evil takes a string containing a Python expression, runs that expression, and returns the result. Like evil 10 plus 5, 2 will calculate 10 plus 20 and return the integer 20.
But the danger is if that string comes from outside.
Exactly. If a user can control the string you pass to evil, they could potentially run any Python code on your system with the permissions of your script. Very risky. Only use it on trusted code strings.
Okay, and exec. How is it different?
Exec is for running full Python statements, not just single expressions. It can handle multiple lines of code, define variables, define functions, run imports, but it doesn't return a value itself. It modifies the current environment.
Like the example, executing a string that sets x and y, calculates z equals x plus y, and prints z.
Right. It changes the state, runs code blocks. Same security warnings applied, maybe even more so because it can do more complex things than eval.
And compile fits in how?
Compile is like a pre-processing step. It takes a source code string and turns it into a special code object. This compiled object can then be run multiple times using exec or eval.
So compile once, execute many times.
Exactly. If you have a piece of dynamic code you need to run repeatedly, compiling it first can give you a performance boost because Python doesn't have to reparse the string every single time.
Okay, moving away from the danger zone to some essential utilities. Sorting and reversing.
Yeah.
Sorted and reversed.
Key difference here is what they return and whether they modify the original, sorted, takes any iterable, and it gives you back a brand new list with the items sorted. Crucially, the original iterable is untouched.
Non-destructive. That's important.
Very. Reversed, on the other hand, doesn't give you a list directly. It returns a special reverse iterator. Another lazy evaluation example.
So you have to convert it, like list, reverse to actually see the reverse sequence.
Correct. It yields the items in reverse order one by one when you ask for them.
Got it. Next up, quick Boolean checks, any and all.
These work on iterables and leverage that truthiness concept we talked about. Any checks if at least one item in the iterable is truthy.
So any 0, false, 1, none.
Is true, because the 1 is truthy. It stops checking as soon as it finds one true value.
And all is the opposite, strict.
Very strict. All only returns true if every single element in the iterable is truthy. If there's even one falsy value, like 0, false, an empty string, none, an empty list, all immediately returns false. Great for validation.
Okay, character stuff. Triochi, HR, and ORD. The bridge between letters and numbers.
Exactly. ORD takes a single character, a string of length 1, like B, and gives you its integer Unicode code point, which is 66 for B.
And TR goes the other way, Ken's 37.
Gives you the character A. Essential when you need to work with text based on its underlying numerical representation, like in encoding or simple ciphers.
And number-based conversions, text, locked, bin. Just handy utilities to get string representations of an integer in hexadecimal base 16, octal base 8, or binary base 2. They automatically add the standard prefixes, 0x, 0o, 0b.
So bin 42 is 0101010, hex 255 is 0xf. Useful for low-level stuff.
Yep, system programming, understanding memory layouts, that kind of thing.
2 more quick practical ones. Format.
Format. This is the function that powers modern f-strings and the .format method. It gives you super fine-grained control over how values are represented as strings, padding, alignment, number precision type conversions.
Like format 3.14159.2f giving 3.14.
Exactly. It's the main tool for precise output formatting. And help.
Just forgetting .help.
Pretty much. If you're in an interactive Python session and forget how something works, just type help and pass it the function or object name, like help print or help list. It prints out the documentation string, docstring for that thing. Super useful.
Can't forget open, the gateway to file.
Absolutely fundamental. Open connects your Python script to a file on your operating system. You give it a file name and a mode, R for read, W for write, A for append, add B for binary mode, etc.
And it gives you back a file object.
Yep, a file object that you then use to read content from the file or write content to it. Like the example shows, writing a string and then reading it back. All file I/O starts with open.
Okay, final section. We're looking at some advanced functions often tied to performance, how objects are structured, and the context they run in. Starting with memory view. Sounds low level.
It is. This is for performance optimization, especially when you're dealing with really large chunks of byte-oriented data, like huge byte arrays or data from libraries like NumPy.
What does it do? It gives you a view into the memory buffer of an object without making a copy of the data itself.
It's zero copy.
Exactly. If you have a massive byte array and you just need to work with a small slice, taking a normal slice, my bytes 1.4, would create a new small bytes object, copying the data. But memory view my bytes, and then slicing the view, memview 1.4, gives you access to the original data in place.
So much faster and uses less memory if you're doing lots of slicing or passing data around.
Precisely. Crucial for high-performance I/O or interfacing with C libraries.
We mentioned object is the ultimate base class. What if you just call object itself?
You just get the most basic featureless object possible. An instance of the base object class. It doesn't do much, but it sort of represents the primordial building block.
Okay. Now into the object-oriented programming OP. Helpers.property. Usually seen as the @property decorator.
Right. @property is the common way to use it. It's Python's elegant solution for managing attribute access. It lets you make a method look like a simple attribute lookup.
So instead of calling myObject.getValue, you just write myObject.value.
Exactly. But behind the scenes, your getter method runs. And you can also define setter and deleter methods linked to that same property.
What's the benefit? The source example mentioned validation.
That's a major use case. In the myClassWithMethods example, the @value.setter method checks if the incoming value is positive. If you try to set myObject.value equals -10, the setter code runs, sees it's negative, prints an error, and prevents the attribute from actually being set to the invalid value.
So it protects the object's internal state while keeping the external interface clean.
Exactly. Encapsulation without awkward get and set method name.
Then we have @class method and @static method. More decorators for methods inside classes.
Right. They change how a method behaves regarding the class and instance. A @class method receives the class itself as its first argument, conventionally named indi_else. It doesn't get the instance.
What's that used for?
Often for alternative constructors, like the createFromString example, a class method that knows how to parse a string and create a new instance of the class from it. Factory methods, basically.
And @static method.
That's even more detached. A static method doesn't receive the instance self or the class CLs automatically. It's essentially just a regular function that happens to be nested inside the class, usually because it's logically related but doesn't need access to instance or class state.
Like the isPositiveUtility function example. It belongs with the class conceptually, but doesn't need self or slice.
Precisely. Just organization.
For inheritance to work smoothly, we need super.
Yes. Super is crucial for cooperative inheritance. Its main job is to help you call methods from a parent class, or more accurately, the next class in the method resolution order, MRO.
Most commonly used in init.
By far. When a child class inherits from a parent class, the child.init method must call super to make sure the parent's initialization logic gets run. Otherwise, parts of the object defined in the parent might not get set up correctly.
Ensures the whole chain of initialization happens properly.
Absolutely. And it works correctly even with complex multiple inheritance scenarios.
Okay, 2 more for understanding the runtime environment. Globals and locals.
These give you dictionaries representing the namespaces. Globals returns a dictionary of all the names, variables, functions, classes available in the current module's global scope. Everything defined at the top level.
And locals.
Locals gives you a dictionary of names available in the current local scope. If you call it at the module level, it might look similar to globals. But if you call locals from inside a function,
You only get the variables defined within that function, like its arguments and any variables assigned inside it.
exactly. The example showed local var2 when called inside a function. It's a snapshot of that function's private workspace. Very useful for debugging or introspection frameworks.
And finally, the modern way to jump into the debugger, breakpoint.
Yep. Much cleaner than importing PDB and calling pdb.setTrace. Just put breakpoint anywhere in your code. When Python hits that line, it pauses execution and drops you into the default debugger, PDB, unless configured otherwise.
Lets you inspect variables, step through code, figure out what's going on right at that point.
The standard, simple way to start debugging. #tag outro.
Wow. Okay, that was a pretty comprehensive tour through Python's built-in function toolkit. Over 50 functions.